Okay, 16 seconds.
Damn it.
All right. Okay. Hey, Lady Ada, get back on the show.
Hey everybody, I'm just trying to catch a cat, and the cat is very slippery. But we're back. It's me, Lady Ada. I'm at my desk. The cat's over there. You can see him if you're watching this on the Hug VR. He's sneaking around. But today I want to just follow up on last night's stream where I was building this programmer tester for an 8-bit AVR, and I have a Arduino Zero programming the chip, and then I want to use the USB capability of the Arduino Zero, the USB host capability, to test do the final test of the board by doing a USB enumeration, basically verifying that the chip booted, the crystal's correct, the USB connector's on proper, like the D- D+ pins aren't shorted, and I have the right bootloader installed. So last we were doing this when I added USB capability, because I got everything going with like programming the chip, but when I added the USB initialization, the Arduino Zero sort of crashed, like it stopped working. And I was like, oh, it's probably this RAM thing. And then I actually spent like another hour, and I kind of poked around, and I learned a little bit more about how ARM, GCC, and ARM processors store user data in Flash, and I thought I'd show it because it's a little different than AVR. It's a little easier in some ways, but you still have to kind of know what's going on. I'm going to also write this up and put it in my M0 sketch notes. So let's go to I guess let's go to the overhead real fast. I'll just show this off because we're not going to really see this again. So this is the Arduino Zero, and this is a mess of wires, but basically I have a bunch of wires connected. Actually, I can remove pretty much all of these because they're not going to be used. Hold on. This is the self-test wire setup, which I don't really need. Move this wire. And then move this wire, These wires I'm not going to use either. Leaving me only. Yeah, I don't need these yet. And I got this all working, and I can always wire it up again later. All I really need for this test is, hold on. Actually, I do need to connect this. Actually, no, I don't. Okay. All I need to connect is the reset line, the S clock, serial clock, MOSI and MISO lines, and this will allow me to program. This basically implements the AVR 8-bit SPI command set to program this chip with. So let's go to the computer, and we'll just see where we were at before. And you can watch the previous stream. I kind of go about like how this actually works. But let me select Zero programming port, and then this port, and then I'll upload this code. So where we were last time is basically you're programming in the fuses and the flash to program this board, so I don't have to use a USB TD in a computer. It's a standalone programmer. And this is an adaptation of the code that I wrote for the AVR like standalone like OptiBoot programmer. So let me hit the reset button. Start from the beginning. And basically it's like, hey, I'm just checking that the 3-volt regulator is okay, and I press the button to start programming. It reads the signature, erases the chip, flashes the boot, flashes the fuses, verifies the fuses, and then where I stopped was USB verify. So this printout here that says USB verify, I don't actually do any USB verification. It's actually just, I think I just wild one here because I'm just waiting to add the USB code. And I added the USB code and it wasn't working, so let's do that again. And so at the very beginning, I'm going to, after I print out my welcome message, I'm going to turn on USB by running USB init. That'll initialize the USB host stack for the Arduino Zero. So let's upload that. this window over here, and then this window over here. Yeah, that's good. Uploads it, and then takes a little to upload. I run it, and then what happens is right after it initializes USB, it should print out that 3-volt logic, but it actually crashes. It never makes it out of USB init, and it doesn't even like. I don't have a watchdog running, otherwise it would probably reset, but it actually just like halts. And so I was like, oh man, I bet it's some RAM thing. And it is a RAM thing. The RAM thing is I'm running out of RAM. And what happens if you run out of RAM is you end up having your memory is divided into two pieces, the top and bottom of memory, and you have your stack, which is the memory needed to run functions and have all the local variables, and you have your heap, which is all your global variables and global data in RAM, and malloc if you use malloc. And basically, if they ever collide, the memory that you're using for data variables ends up overwriting the data that you use for running your functions and like your stack pointer and stuff, and your program crashes. And that's what on Unix or Mac you get a seg files. On Windows you would just usually error and quit. But this happens a lot when you run out of memory. So the thing you want to do is not use memory. And on an 8-bit processor like a Atmega 328, you only have 2K of RAM. But in this case, I have 32K of RAM. But when I'm normally writing the boot, this is the image for the bootload code. You can see all this is hex data. This is about 25K of data, and this usually is stored in the flash memory with progmem, right? Progmem usually means put this in program memory. And I just copied this, basically copy and pasted this code and ran it on the Arduino Zero, and it worked just fine because I have so much memory that even though it's actually not putting in program memory, it's ending up putting it in RAM instead. Like it should be putting in program memory, but it's not. So this is the bootloader code called image32u4 boot. And what I can do is say, hey, the address of image32u4 boot equals, and then print out the address, so ampersand address of, in hex. Let's compile it. It might need me to cast this. Pretty cool. Yeah, it doesn't like me to do this. Okay, so you want to cast this to be a UN32. Remember, it's a 32-bit processor, so you cast your pointers as 32-bit. You don't actually want to do pointer math, if you can avoid it, like by casting to ints, but if I'm just printing it out, it's fine. So print it out, and it says the address of this data is at high word 2000 and then 6. So it's basically 2000006. So it's near the beginning of the 2 section of memory. So if you open up the Cortex M0 datasheet for the SAM21, and you scroll down to the memory map, which is
Are you
here.
You're auto-tuning it tonight.
Yes. So here it is. I knew it was here somewhere. So this is a physical memory map. I mean, physical. It's not true physical. There's not a slot. It's mapped around. But internal SRAM starts at that address, that 2 million whatever hex 2000, and that's not what we want. That's the wrong location. I mean, it's the right location if you want something in RAM, but it's not the right location if you want to store it in Flash. If you want to store it in Flash, the address needs to be starting with 000. It should be in the very, very low address. But what's really interesting is on an AVR, like an 8-bit processor, as far as I remember, the pointers that you have for the chip can't tell whether the address is in Flash or RAM because you don't have enough, you don't have enough bits in your address space. When you have 32 bits of address space, you're just like, I'm just gonna give you like, oh, like a million bytes over here and a million bytes. Like it's like totally cool to like map anything to this 32-bit space rather than having special registers or special address spaces, because you just have like so many bits. You have 32 bits of memory, like you're addressing ridiculous amounts of memory. So it's like you can just section off whole areas for like SRAM gets like from 2 up to 4. So do the math. It's like a lot of, I can do it for you if you want, but you do the math. It's like 1000 hex bytes. It's a lot of bytes. So, but this address is incorrect. It shouldn't be here. It shouldn't be at the 2 area, the internal SRAM. It should be in internal flash. So it turns out like I wish the compiler would have warned me, but it turns out progmem is actually completely the wrong thing to use. You don't use progmem, you want to use const, which on the AVR doesn't do anything. You can't use just const on the AVR. You have to use const and then progmem. That's cool. So let's try compiling it. We set this to be a const, and it's going to, it might complain. Oh, this is something kind of interesting. I did notice this. Maybe I don't know how to do like externs, but I couldn't actually. Let's see, this target image, hold on, this pointer also has to be different. I think, yes, this is a, I don't know if it's a const image pointer or image pointer const, I'll figure it out. Compiler will tell me. Yeah, it doesn't, it's like for some reason it doesn't, I'll figure this out, but something with AVR GCC is like, I don't like it when you have an extern pointer to extern reference to a const. So like, just for now, I can figure that out later. I'm just going to cut this and make a new header file. And I'm just going to put this in the header file, and then I'll just include this. It's cheating, but whatever. Doesn't matter because I only use it in one location anyways. So comment this out. Let's see if I can. I also have like I ended up doing more work, so I can always go back to the completely finished one if I don't remember what I did. Okay, so this time it includes fine, like a whatever deal it had. So upload it, and we'll see. It should now put it in Flash because it's a const. You know, const. Keeping it const. And there you go. So the address of this thing is no longer in the 2000s zone. It's now in the 7F14 zone, which is fine. I mean, like, you have a lot of program flash used for all this other stuff, and this gets chunked at the end after the bootloader, after the firmware. So now you don't have to worry about like, oh my God, I'm running out of space, because it's being stored here. And what's really neat about, because you have these 32-bit pointers, the compiler and the compiler and like the parser and everything, you don't have to do the PGM read byte or read word or read far word. Like, it doesn't matter. Like, it knows like, oh, I'm reading it from Flash. It automatically does the right thing. So that's one of the nice things about ARM processor. So the last thing I'm going to do is open the, oh, I can't scroll. Weird. Okay, I'll open it by hand. Oops. 0, and then I wanted the USB descriptor simple. So let me just verify that this works. So program this, flashing, fuses, looks okay. But then when I get to the USB verify state, instead of halting, I would like it to do this. So let's go go to USB verify. And then, of course, I have to add the self-test mode as well. While one to USB task, if the USB task is running, get the descriptor, got return code, print the vendor, and then also print the ID product. Okay. So while it's compiling, any questions?
Let's see. No questions yet. There was, I mean, besides like what you're doing.
Oh, like in general, or? Oh, I have a.
Yeah. Well, I think is there a general description? So flash storage on ARM processors is a little tough.
Basically, it's like I'm how to get large chunks of data to be stored in flash memory, not RAM memory. So like the image, the hex image of the code I want to flash, I don't need it to be in memory RAM. I need it to be in flash. Hold on, print status. Did I delete something by accident? I think I deleted something by accident. 1 second, let me. Oh, I think I just deleted something, or I didn't.
Okay, I have another. I have a question when you're ready.
Yeah, 1 second. So this is. Oh yeah, hold on. I need to finish this loop. There you go. Okay.
All right, ready for another question?
Yeah.
Okay, in the SAM R21 video, you put all the voltage pins to 3.3, but no documentation says that a VDD core are connected to ground using noise capacitors. Is there a reason for this?
I don't remember off the top of my head. I was kind of going by the eval board. I kind of made a mistake. It's common for the first version I make to have errors in it. I believe I did sprinkle a bunch of capacitors on there, but I'm pretty sure that the core voltage was 3.3 volts, but it could have been 1.8. I think it was 3.3 though, but I have an onboard regulator, and I usually have pretty good regulators, so if they're expecting 3.3 volts, like I just usually tie them to 3.3, but I think I was just going by the eval board. Okay, so I'm gonna try programming this chip again. Note that the address changed, it was 7F. And now it's 8910. That's because the program got bigger. But this time, after it's done, I did a USB verify, and I did identify that I got VID 239A and PID 0C. So that's pretty much what I expected. That means that USB enumerated. So this is a really great way to just like do a full functionality test without a computer. I have a chunk of code that I'm missing here where I actually do pin checks and I check the voltages of everything. But this is just like getting the memory that you want to program into a chip stored in flash. We have 256K flash, so like plenty of space. And then once that's done, you program it into your chip, verify it, program the fuses, and then reset it and do the USB test. So you know that you basically programmed in the right code and everything works out pretty well. So this is kind of the beginning of a tester. I will continue working on this, but historically I used the Arduino Mega USB, the Arduino Mega 80K, and since that's kind of discontinued and no longer made, I'm going to start moving toward using the Zero. And now that I figured out how to get the program in memory, it's like I can store multiple images if necessary.
Okay. All right, another question. So you could use an internal memory as cache to the external bus.
Yeah, but it's not really a cache because it's read-only. So it's ROM, not RAM. So it's only good if it's like you have, you want to display something on a TFT, you want to store fonts, or you want to store bitmaps, or you want to store calibration tables, or like a sign table. That's stuff that you should keep in program memory.
Okay. Where will the serial output show for the testers?
There actually won't be any serial output. I'm going to have NeoPixel, and it'll just change colors. and the color will indicate what it's doing, like red for failure, green for pass, blue for programming state. I might have a LCD, like a character LCD or an OLED if I really need to have display output, but the whole process only takes like 5 seconds, and the yield we have is very, very good. So if something fails, it's probably like shorted pins, something that's physically visible, in which case the person testing would put it aside and then it would get reworked and then retested. But our yield tends to be like 97, 98% for boards like this, so I'm not too worried. Like, making the tester longer is less effective than making it very fast and just failing on any error.
Okay.
Like, there's not that many parts either. It's not like a gigantic motherboard where it's like there's so much to test and so much to go wrong.
All right, this one has nothing to do with what you just showed, so maybe I'll try to answer it. Someone has a fairly large open source education project coming. Have any contacts interested in doing some work taking part which might involve a project in remote areas, possibly Africa? We don't have any contacts, but the Engineers Without Borders folks might be someone to try, because I think they do lots of things anyways. Mm-hmm. And then there was, on Make, this is a really long time ago, because I believe there was a maker fair in Africa, and there was Africa Makers. I don't remember the name of the site, but search on the MakeZine site, because I remember covering that a million years ago when I wore a different hat at Make.
Yeah.
And so I would check that. And I remember there was a person, and I forget his name, but he was leading some of the efforts, and there was a maker fair there. Okay, next up. This person is beginner electronics, and they would like to start making custom Arduino boards, and they'd like to know how to program the ATtiny85 and Atmega 328 with a micro USB port.
Well, you can look at the Trinket design or the Pro Trinket design, which uses those 2 chips, but you still have to program it. You can bootload it over the USB, but you have to program it with the USB TV. This is that initial stage of just getting the bootloader on there.
Okay. And to the person who's working on the open source, I don't know what camera to look at. I got 8 cameras right now. We have like 9 cameras right now. For the person who's looking to enlist help, you can always post up on the Adafruit jobs board, adafruit.com/jobs, and Lady and I approve those, so it's no, there's no noise. It's just straight up legit stuff.
Legit.
And people can contact you that way. And if you run into a jam, we can do a blog post for you. Just email pt@adafruit.com and send me the text exactly what you want on there and some contact info, and we'll post it up, and someone can maybe get a hold of you. We have a lot of people who read our blog. Our website is up to 12 million page views.
That's pretty cool.
A month. Yeah. Okay.
Nice.
Let's see. I think that's everyone and everything.
That's it for me. I'm set. I just wanted to show off.
Yeah, that's everything.
I got my thing working.
Yeah, I'm gonna do a quick little video of this setup, because this is
Mac setup.
Well, this is a little historic. So for the folks watching, and I'll do the video as I do this, because I think this is a big deal. All right, come on. Ah, man, it's not what I wanted.
Phones.
Really?
Nope.
Come on.
Phones.
All right.
Not likey.
Yeah, so I'm gonna do a video, and I'll start the video. Oh, it's Eric from the Hat Sensor show until ages ago. Oh yeah, Learjet, the Basil Garden. Oh yeah, wow. That guy has tons of cool projects. Hello. Okay, that's true. All right, so I'm going to start over. I'm going to start here, and then I'll work my way around, so everyone can see what's going on here. Okay, so we are broadcasting live, and then we also are broadcasting on Hug VR, and this is live, and then we have this is the camera that it uses, and that's a 360 camera, and it's in live mode. And then we're broadcasting on Twitch and YouTube, and then we're broadcasting on Meerkat and Periscope, and then Lady Ada is here, and we're still doing all of this right now. So I'll post this up on YouTube, and this will be archived. But as folks can see, yeah, we got a lot going on. This is Twitch, and then here's YouTube. So this is This is happening.
Happening.
Yeah, and Hug VR is the service that we're using to do the VR stuff, which is, I've never seen this before, and that's neat. And occasionally you get to see stuff. And then one of the things that we also try to do here is we also try to have cat cam. And here's cat cam. Here he is.
The cat.
Yeah.
The cat stopped.
Hey, cat.
Hey.
Yeah, he's here. He's there. Cat cam.
How did you get
Okay.
the cat pointed at him? Which
What?
camera is
It's the
that?
camera that's over there. There's just cameras everywhere. Okay.
I can't even tell which camera this is.
Yeah, I know. All right.
Oh, you just tossed
So-
it in. Okay.
Yeah, so that's that. So there's camera inception here.
Cameras.
Yeah.
Okay.
Okay. Woo! All right.
Yay.
Okay, bye-bye.
Later, everybody.
Okay, so
camera
Lady Ada,
breadboard.
that's the end of the show.
Yeah. No, I'm done. I'm putting away my transistors.
Yeah. Okay.
This is like the that's like the engineering equivalent of like when Mr. Rogers took off his sweater and
Yeah.
his shoes and stuff.
All right. We're outie.